Okay, welcome back to our calorimetry notes. This is part two, and broke it up because these problems can get a little bit long and challenging. So in part one, we went through the first two pages of notes, and now we're looking at the last page. And this is a pretty daunting example problem, so let's go through this. So I've got a 200 gram, 100 degrees Celsius piece of metal. And I think drawing a quick little picture over here might help us keep this straight. So here is my chunk of metal, all right? And I know the mass of it and I know its temperature. We drop it into a cup of water containing 150 grams of 20 degrees Celsius water. So blunk goes into the container with water. And actually, this would be completely submerged. That's not a very good drawing there, but I'm just drawing in a small space. And so we've got a 100 degree chunk of metal, which is hot, and 20 degree water. Now, you know and I know that the chunk of metal, a 100 degree chunk of metal, is going to cool off. And so that is going to be losing heat. And we just figured out that there's a formula for heat, and it is mc delta T. So if you think through this, all right, the water, right, and the metal, they're going to get to the exact same temperature because they're in contact with one another. So the amount of heat that the metal loses has to be equal to the amount of heat gained by the water. So what we're going to do is we're going to say, we're going to make basically this expression happen. All right, the amount of heat is Q equals mc delta T, right? The amount of heat that's lost by the water equals the amount of heat gained, the amount of heat lost by the aluminum is equal to the amount of heat gained by the water. Now, the reason that there's a negative sign here is you think about the amount of heat lost by the metal, that's going to be negative. And if we think about the amount of heat gained by the water, well, that's going to be positive. They're going to be equal in terms of their absolute values. So all we did was we said, hey, let's take the opposite of the sign of this critter, all right? Because I know that the opposite of a positive is negative. That's how we get away with saying this algebraically is equal to each other. I could have just as easily said, let's make the opposite of the amount of energy lost by the metal equal to the amount of energy, the amount of heat gained by the water, right? So the thing that you just have to do with a problem like this, where you have not just one object, but literally two objects, one thing, the metal, which is losing, and one thing, the water, which is gaining energy, you just have to decide that one side of the equation is negative and the other side is left alone. Doesn't matter which side. All right, so here we go. We look at the problem and we think carefully about what we know. And if you kind of think about it as sort of two sides, there's a metal side and then there's a water side. It's going to help you keep this stuff a little bit straight in your head. So what do I know? I know the mass of the metal is 200 grams. I know that the metal dropped by 55 degrees Celsius. Again, that change in temperature is final minus initial. Now, what we don't know about the metal, and that's what we're being asked to find in this problem, it says calculate the specific heat of the metal. So we're going to leave C as unknown, since we know that the amount of heat associated with this metal is mc delta T, right? I know the M, I know the delta T, and hopefully C is what we're going to end up being able to solve for. We come over here and we look at the water side of things. I know how much water I have. I know that the water started out at 20, so it's always final minus initial. So the water gained 25 degrees Celsius in temperature. Remember, temperature is not heat. Temperature is a measure of the average kinetic energy of the particles. But if we want to convert that temperature number into a heat quantity, we've got to use Q equals mc delta T. And the nice thing about this, so on this side of the sort of problem, we know the mass of the water. We know the specific heat of the water because the specific heat of water is always 4.184 joules per gram degrees Celsius. They're wacky units, but it makes sense when we look at it from this perspective. I want my grams to get canceled out, and I want my delta C, my change in temperature, to get canceled out. So when I multiply these guys all together, what's left is joules. So at this point, we come down here and we say, all right, plug in what we know. And what we know is lots and lots of stuff. So for the water, we can go ahead and figure out that on the water side of things, the amount of heat, the amount of energy associated with that side of the equation is this number, all right? And then we say, okay, so if the water gained this amount of heat, all right, we know that that heat was gained from the metal, all right? So the amount of heat lost by the metal had to be this quantity, all right? So notice how we just changed the sign on it, all right? Because this one gained, because this one lost. At this point, we then say, all right, we now know the amount of heat associated with that particular chunk of metal, 200 grams, losing 55 degrees of Celsius temperature. And at this point, it's just doing some math, Q equals MC delta T. And so we end up seeing that the specific heat of metal is 1.4. And so what does that mean again? This means that it's only going to take 1.4 joules of energy to change 1 gram of the metal by 1 degree Celsius. Now that's a fairly small number compared to the water, which was 4.18 joules, right? That's what's going to change 1 gram of H2O by 1 degree Celsius. Okay? Now, these aren't the easiest problems, all right? But hopefully, this at least gets you started, and maybe you'll join me for class time tomorrow. I want to say that that is Friday, March 27th, and I will not only have help videos posted on the calorimetry problems that I've assigned for today, but during class time, we'll go over as much or as little of those calorimetry problems as you need, because they are tricky. And with that, I hope that all of you have a wonderful day. And I hope to see a number of you during class time Friday, March 27th at 9 a.m. Take care and be well. All right. Bye-bye.